Okay, hi everyone. I'm Tal Malkin. This is the first lecture after my introductory video. As a quick reminder, a language is decidable if there exists a Turing machine M such that when X is in the language, M accepts X, and when X is not in the language, M rejects X. In other words, M always halts. So this M is a decider. Okay. And the language L is recognizable, Turing machine recognizable, if there exists a Turing machine M such that when X is in the language, M accepts X, and when X is not in the language, M either rejects X or runs forever on X. Okay, and we are asking at this point in the class, which languages are not decidable or maybe even not even recognizable? How do we prove a language is not decidable or not recognizable? And we've already seen some answers to this. So in particular, one answer we've seen is that almost all languages are not recognizable. Right? And the way we saw it, recognizable, is by claiming that the number of recognizable languages is countable, whereas the number of the cardinality of all possible languages is not countable. So just to quickly show why this is the case. So first of all, the set of all strings is countable. Right? Because we can enumerate all strings. In some order, let's say in lexicographic order or any order. So the set of all possible strings is countable. Moreover, every Turing machine can be represented, or every algorithm, every Turing machine can be represented by a string. Whoops. Okay. Every Turing machine can be encoded as a string, right? Which is a very important thing. And so therefore the set of Turing machine is a subset of the set of all possible strings, and thus the set of all Turing machines is countable because it's a subset of strings. And therefore the set of all the languages such that L is recognizable is also countable. Is countable. Right, because each Turing machine recognizes exactly one language. The same language might have many Turing machines, but each Turing machine recognizes just one language. And so the set of all recognizable languages is countable. On the other hand, the set of all languages is not countable. Of all languages, which is what? It's just the set of all the subset of sigma star, right? A language is just a subset of sigma star. This, in other words, this is the power set of sigma star. And this is not countable. If you recall in an early lecture talking about diagonalization, so we've shown this via diagonalization. So this was in an early lecture. You saw that the power set of infinitely countable set cannot be countable. And we showed this via diagonalization, similar to Cantor's diagonalization. And so, you know, there are uncountably many languages and only countably many of them are recognizable. Therefore, almost all languages are not recognizable. So this is one thing we've seen. Another thing you've seen is a specific example or a couple specific examples for languages that are not decidable. Okay, so we've seen specific languages that are not decidable. So one of them was ATM, which was defined as the set of all the MW, where M encodes a Turing machine, and M accepts W. You've also shown it for the halting problem. Okay, so this language is not decidable. And just a quick recap of the proof. You've already seen this proof. I just want to recap it because I want to make the point that this same proof is in fact a proof by diagonalization. So assume towards contradiction, there was a Turing machine, let's call it accept, that decides ATM. Well, if I had such an algorithm, I can construct another algorithm, B, as follows. And this is B, so on input M, it gets as input a description of an algorithm, and then it just runs the supposed decider. So if I run the decider on M and itself, and if it out, and then I flip the answer. If it outputs yes, reject, else accept. Okay, and this program B, if such a decider accept existed as an algorithm, then this would be a valid algorithm right here. And now we can ask ourselves, to get a contradiction, we can ask ourselves, what does B, how does B behave on the program B behave when it gets its own code as an input? Okay, so does B accept when it gets its own input? And well, if the answer is yes, we get a contradiction. And if the answer is no, we also get a contradiction. Right? Because if it accepts itself, then it should reject itself. And if it does not accept itself, then it should accept itself. Okay, and so therefore, this assumption that this algorithm exists is not true. So I just wanted to point out that this is called diagonalization technique. And the reason is you could view this same proof as diagonalization in the following sense. You can think, let's put all the Turing machines here in order. There are countably many of them, as I said, so you can put all of them in some countable order. These are all the Turing machines that say, take as an input code of some machine and then either accept or not. Okay, and let's look at all possible inputs, input Turing machine encodings of Turing machine. Okay, and we will put in this table either a yes or a no. So in location ij, in entry ij, we'll put a 1 if mi accepts the encoding of mj, and we'll put 0 otherwise. Okay, so we can think of it like this. So given this, if I had a decider for the acceptance problem, if I had a decider for ATM, I could then construct a Turing machine B, which would look at the diagonal and disagree with it, do the opposite for each diagonal. Now I can build a B, a Turing machine B, such that, which is, I will not write it again, it's exactly the one we saw before. This B here. It exactly disagrees with the diagonal. So on every input M, it checks whether M accepts M and flips it. And so now it's not possible that B is in any row here, because if B was in some row, well, what happens in the diagonal? It needs to flip it. Okay, and so such a B could not exist, and therefore no such decider exists. So there's no, so ATM is not decidable. You also showed that the halting problem is not decidable, and that was also using diagonalization technique. Okay, so using diagonalization, we've shown that ATM and also the halting problem is not decidable. Okay, so now we want to talk about how to prove that other languages are not decidable. So you could try diagonalization maybe for some other languages, but in general, it will not always succeed. And we would like to prove for many other languages. And the key concept here that will allow us to do it, so the key concept that will allow us to prove additional languages are not decidable is using reductions. Okay, so informally speaking, so to prove some language B is not decidable, once you already have some languages that you know are not decidable, you can use them in order to prove additional languages are not decidable. You could do the following. So assume towards contradiction that it was decidable. Assume towards contradiction that B is decidable. And then use the decider to construct a decider for ATM. Okay, or for any other language that you already know, or another language, any language that you already know is not decidable. That you know is undecidable. And this would be a contradiction. Okay, so you're assuming that there was a decider for B, I will construct a decider for ATM. And I would say, I already know that ATM is not decidable, therefore there's a contradiction. Okay, this is the notion of reduction, and we will see examples. So let me say, okay, let me define. So we say a language A is reducible to B, and we denote it like this. I'll discuss this notation in a minute. If given a decider for B, we can construct a decider for A. Okay, so this is in general, it's called a Turing reduction. This is the reduction I'm defining here. I'm not going to define it fully formally. You will see in a later lecture a formal definition of this Turing reduction using, Turing machine, a formal description of a Turing machine that can call the decider for B. So I will not define it more formally than this, but I want to say something about this notation. This notation intuitively means A is easier or equal to B. So in other words, if you know how to solve B, you will also know how to solve A. Okay, and if A is very hard, then B is even harder. Okay, so we use reductions all the time, both explicitly and implicitly. They can be used for for constructing algorithms. Think about writing a code for something in a programming language and you call some function. Okay, so if you had some solution for B, you can call it as a function in order to construct a solution for A, right? For example, if you have a way to multiply integers, you can write a program that takes an integer to the power of another integer by calling the multiplication subroutine. Okay, this is a way to use it to construct algorithms. But here in this case, we will use it in the opposite way, to show that if there exists no algorithm for A, then there cannot exist an algorithm for B. Why? Because if there was an algorithm for B, then we could construct an algorithm for A. Okay, so let me show you an example of where it's used. So let's define the following language, ETM. E stands for emptiness, the emptiness problem for Turing machines. It's the set of all encodings of Turing machine where M is a Turing machine, and L of M is the empty set. In other words, the set of all Turing machines such that the Turing machine accepts no string, never accepts any string. Okay, so my claim is that ETM is not decidable. Okay, this is what I want to prove. And my proof will be by reduction from ATM. Okay, so I will say assume towards contradiction that I had some decider for ETM. That there is a decider, let's call it, I don't know, R, deciding ETM. Right, what does it mean? R will get as input an encoding of a Turing machine, and if the language is empty, it will output yes, accept, and if the language is not empty, it will output no, reject. That's what it means to have a decider. So now I will use R to construct the following decider S for ATM. Okay, and this will be my contradiction since I know that ATM is not decidable. Okay, so good. So what will I do? So here is S. So S is supposed to decide ATM, and so the input to S is the input of the form that it expects for an ATM. Okay, and what S will do is the following. So construct. So S gets an M and an W and wants to know whether or not M accepts W. What it has at its power is a supposed, think of it as, you know, you have a friend, R, who can answer questions only about ETM. Okay, you want to use that in order to answer whether M accepts W. So what we will do is we'll construct a description of a Turing machine, okay, an encoding of a Turing machine M prime, where M prime, we'll discuss in a minute what M prime is. We will construct it in such a way so that this reduction works. What do I want to do? I want to specify how M prime behaves on every input. I want to construct this M prime. And what I want to do is then run, so I will construct M prime in a second. We want to run R on M prime and use the result. So our goal is starting from MW, construct a new Turing machine M prime, such that if I know whether or not M prime accepts the empty language, then I know whether or not M accepts W. Okay, so there are various ways to do it. Here's one example. Here is one way to do M prime. So M prime on input X, this is the program specification. I will say just ignore the input, ignore input, and just run or simulate M on W. Okay, so I have M and W, I hard coded into the description of M prime, and I just run M on W and do the same if, and output same. This means I just run M on W. So whatever my input is, I ignore the input and just start running M on W. If M accepts, I accept. If M rejects, I reject. Okay, and obviously if M looped forever, this program would loop forever. Okay, so now I run R on M prime, and if it accepts, I reject. And if it rejects, I accept. Okay, so this is, this S here is my decider. I claim that this is a decider for ATM. This is what we will show. We will show that this is a decider for ATM, assuming that R was a decider for ETM. Okay, and that would be the contradiction. So let's see, why is this the case? Well, if MW, I want to show that if MW is in ATM, then I accept, and if it's not in ATM, then I reject. So if MW is an ATM. What does it mean? It means M accepts W by definition of ATM. Which means what will M prime do? M prime on every input X will always accept, right? Because it just runs M on W, which accepts. Means M prime accepts all inputs. And in particular, the important part is the language of M prime is not empty. In fact, it's all strings. And since it's not empty, then by assumption, R M prime rejects, and therefore my algorithm S accepts. On the other hand, if MW is not an ATM, then M does not accept W. So M, I don't know, either rejects W or runs forever on W. I'm ignoring here the case of the encoding was not a valid encoding. These are easy to check, so we're ignoring them. So M either rejects W or runs forever on W. What does it mean about M prime? It means M prime where on every input X, it does the same thing that M does on W. So M prime either rejects all inputs or runs forever on all inputs. In any case, the language of M prime is empty. It does not accept any string at all. And therefore, by assumption, R of M prime accepts, and therefore S rejects, because that's how I constructed my S. Okay, so I proved that S decides ATM, which is a contradiction. And thus no such R could exist. So this is a very common proof structure and proof techniques. You want to make sure that when you write an algorithm, every line is in fact algorithmically implementable. And indeed, an important point to note is that when you're given input MW, you construct the code for M prime, you don't run it on any inputs. So I don't mind if M prime is not a decider. This is fine. What I need to show is that I can write the code for M prime in finite amount of time. And indeed, it's easy to write this code, right? I just write the code that on input X, ignore input, and now I copy the code from M on input W. Okay, so I just need to write, there's a difference between running M prime and just writing the code. I want to write the code for M prime. Why? Because I want to give it as input to my supposed decider R, which will tell me whether or not M prime accepts anything at all, and which will help me figure out whether or not M accepted W. Okay, so now we know that ETM is not decidable as well. Let's see another couple examples. Let's define the following. The equivalence problem for Turing machines is the set of all strings of the form M1, M2, where M1 and M2 are Turing machines that recognize the same language. L of M1 equals L of M2. So the question is, I'm given two Turing machines and I'm claiming it's not decidable. I'm given two Turing machines and I want to know whether or not they behave the same way, whether or not they recognize the same language. So I claim that it's not decidable. Okay, so there's no algorithm that can do that in general. By the way, this is an example where it's clear that it's very, would have been very useful if we could have an algorithm that decides this, right? For example, if I want to grade some homework in a programming class and I want to know whether your program does the right thing, if I could write my own program solution and if I could write an automatic algorithm that checks whether my program and your program do the same, that would immediately tell me whether your program is good or not. Okay, but unfortunately, this is not decidable. And here is the proof. So we will show a proof. So there are various ways to do it. Also, by the way, for the previous proof, there are various ways to do it. I will show it by reduction from ETM, because we already know by reduction from ETM. We already know, we just proved that ETM is not decidable. So now I can use this fact to prove the equivalence problem is not decidable. So assume towards contradiction that it is decidable, that the equivalence problem is decidable with the decider R. So let's say I have a decider R that decides it. I will construct a decider S for ETM, and that would be a contradiction because ETM is not decidable. Okay, so now think about, you have an algorithm that can always answer whether or not two machines are equivalent, and you want to write an algorithm that solves the emptiness problem. Okay, that given a machine knows whether or not it's empty. Well, what I will do is I'll just check whether my given machine is equivalent to a machine that accepts the empty language, and that will solve the problem, right? So here is my S. So an input S is supposed to solve, S will solve ETM, will decide ETM, assuming R was a decider for the equivalence problem. So an input M, first construct the code for some machine I'll call M empty set, where M empty set works as follows. I'm using blue to denote I'm just writing this piece of code. I'm not running it on anything. So M of X on input X, reject. Okay, this is a very simple construction, a very simple machine that rejects all inputs. Okay, now run R, which is supposed to decide equivalence on my input M and on this new machine M empty set that I constructed. If it accepts, accept, and if it rejects, reject. And if R was a decider, then it always answers and always answers correctly. And now I claim that S is a decider for ETM. So if M is in ETM, this means that L of M is empty set, which is the same as the language of this machine here that rejects everything, which means R accepts, which means my S also accepts. And if M is not an ETM, everything is, in this case, was if and only if. It was all if and only if. R reject, which is S reject. So this is the proof of correctness, what I wrote here. So S decides ETM contradiction, right? Because we already know that ETM is not decidable. Let me give one last example of reduction that I'll show directly. So in general, the idea in these reductions is that you have to take your input and massage it into an input for the language you assume you have a decider for, okay, in a way that will help you decide your new language. Okay, so let me give a last example, which will be the following. So regTM, we're given, this is the language of all encodings M of a Turing machine, such that M is a Turing machine and the language of M is regular. Okay, so note, I'm not talking about given a DFA. If I'm given a DFA, obviously the language is regular. I'm talking about given a Turing machine, a general program. But I want to know if it happens to be the case that the language recognized by this Turing machine is a regular language or not. And I claim that this is not decidable. And I will show it by reduction using the technique we saw so far. So I will show it by reduction I'll show it by reduction from ATM complement, just for a variety. In the textbook, it's shown by a reduction from ATM, which is slightly different than the reduction I will show. But I'll do by reduction from the complement of ATM, which, by the way, we also know is not decidable, right? We've shown, in fact, that it's not recognizable. We've shown in previous lectures, and we'll get back to it later. Okay, so what will I do? So assume towards contradiction that R is a decider for this class. So R gets as input a Turing machine and tells me whether or not, tells me yes if it accepts a regular language and no otherwise. And I will construct a decider S for ATM complement, which is the set of MW such that M does not accept W. Okay, as I said, I'm ignoring wrong encodings because they're easy to deal with separately. Okay, so here is S. What will S do? So on input MW, S wants to call the decider that R that it has. And so it has to construct a description of a Turing machine M prime, where we'll describe in a minute what M prime does. But what I want to do is now I want to run R on M prime. So I somehow want to construct M prime so that the language of M prime is regular or not regular, depending on whether or not M accepts W or not. Okay, this is what I would like to do. I will say something like this. So M prime will work like this. So on input X. So I will use the fact that I know some language is not regular. So let's say this. So if X is of the form 0n, 1n for some n, I will do one thing, and else I will do another thing. If else is not of that, if X is not of that form, I will do another thing. So what I want to say is I will want to do it as follows. I want to run R on M prime, and if it accepts, accept, and if it rejects, reject. That's what I want. So I better make sure that if M, that if M accepts W, I get a non-regular language. So let me try this and see if it works. If it doesn't work, we will change the construction. Okay, so if X equals 0 to the n, 1 to the n for some n, then I will say accept. And else, if it's of a different form, I will run M on W and output the same. Okay, so my goal is to create a machine M prime. I know that the language 0n, 1n is not regular. Okay, so let's see if I wanted to reduce to ATM. Let's say I wanted to reduce to ATM complement. So if MW is an ATM complement, then M does not accept W, right? And therefore, what is the language? The language of M prime is the set of all the 0n, 1n. Right? Why is this the case? Because on these inputs are always accepted. All other inputs will not be accepted if M does not accept W. Okay, so these are the only inputs that are accepted, which means it's not regular. Okay, which means R reject. Okay, so let me flip the answer here so I get the correct answer. Okay, it accepts reject, and if it rejects accept. I'm flipping the answer just because I wanted a reduction to ATM complement, just because I wanted a different language. So if M prime is in RecTM, then R rejects, which means S accepts, okay, as we wanted. And if MW, again, it's all if and only if it's not an ATM complement, then M accepts W. And then the language of M prime is in fact the set of all possible strings, right? Because the strings of this form are accepted, and strings that are not of this form are also accepted because M accepts W. Okay, and this language, sorry, this was not in RecTM, and this language is regular, right? Obviously, sigma star is regular, which means R accepts because R is a decider for RecTM, which means S rejects. And I proved that, so S is a decider for ATM complement, which is a contradiction. Okay, and therefore RecTM is not regular. So you have now another language that you know is not regular. Let me just comment that so the way I constructed the reduction, I had to flip from accept to reject and from reject to accept. Let me show an alternative proof. Just sometimes it helps just to show you a different proof. Alternative proof, very similar. I'll construct M prime differently. So for S prime, here is an alternative on input MW, construct a different M prime. M prime will do the following. So on input X, good. On input X, I'll do the following, sorry. On input X, I'll do the following. So if X is of the form, obviously we could have taken any language that we know is not regular, but let's assume this is the language that I want. If X, this is the language I'm using, 0 to the N, 1 to the N, then run M on W and output same. Okay, meaning if M accepts, you accept. If M rejects, you reject. If not, you loop forever. And else, if X is of a different form, I reject. So the reason I wanted to give you this alternative proof, let me just complete it. Now run R on M prime, and if accept, accept, and if reject, reject. You can show exactly the same way as above. You can show that S is a decider for ATM complement, and it's a contradiction. Good. The reason I wanted to give you this alternative proof is that we will see later that it sometimes helps to have a reduction that does not flip the output, that just calls it once and doesn't flip the output. We'll talk about it later. It has some advantages. And in fact, this particular language RegTM is not only not decidable, it's also not recognizable and not co-recognizable. Okay, and these two alternative proofs can be used to prove both of these things I just said now. But in any case, the idea in everything we did, an important part is to note that I never ran this M prime. I just need to be able to write this piece of code algorithmically and then run my decider on it. Okay, so this is a new way, using reductions, a very useful way to prove a language is not decidable. What we will do in following lectures, there are two things coming up. One is Rice's theorem, which will sort of include several of these examples we gave here and many, many more examples in a generic way. You don't have to prove separately for each language. It's a general theorem showing something very strong about a whole set of languages. Basically all the interesting languages of the form, all the Turing machines, such that the language of the Turing machine satisfies some property. So we will show next time that all such things that you would want to check about a program, none of them are decidable. This is Rice's theorem. And then we will go on to discuss a special case of reduction called mapping reduction or many-to-one reduction, which allows you to prove that many languages are not recognizable. Okay, so we will do this next time. Thank you.